Physics separates how objects move from why they move. Kinematics provides the geometric framework to map that movement, tracking the mechanics of a path while setting aside the forces that cause it. To measure motion, we must first establish a baseline. Because movement is never absolute, every calculation requires a defined frame of reference to serve as a fixed coordinate system. We define an object as being in motion only if its position changes relative to that established frame. If the coordinates remain constant from the observer's perspective, the object is at rest. Mapping these changing coordinates requires dividing physical measurements into two distinct categories: scalars and vectors. A scalar quantity is defined entirely by its magnitude. Measurements like mass, time, or temperature provide a size or amount, but carry no information regarding spatial direction. Conversely, a vector quantity is only fully characterized when both its magnitude and its explicit direction are specified. While everyday language often treats movement as a simple scalar, physics requires vector modeling to accurately track how an object navigates through three-dimensional space. We see this distinction clearly when measuring a journey. Distance is a scalar that counts the total cumulative path length traveled, regardless of the direction taken. Displacement, represented by the symbol s, is a vector. It measures only the straight line change in position from the starting point to the final destination. If an athlete runs exactly one lap around a 400-meter track, their total distance is 400 meters. However, because they return to their starting coordinates, their displacement is 0. This logic scales up when we measure how quickly these properties change over time. Speed serves as the scalar metric, calculating distance over time to show how fast an object moves along its total path. Velocity is the vector metric, defined as the rate of change of the displacement vector. It specifies both the rate of travel and the direction of that travel in liters per second. Because speed lacks a directional component, an odometer alone cannot determine an object's final location. Only vector mathematics can definitively predict a final position. When velocity itself changes over time, we introduce a new vector, acceleration. In physics, acceleration occurs whenever there is a change in velocity, whether the object is speeding up, slowing down, or merely changing its direction in space. This change in meters per second, measured over each second of travel, gives acceleration the SI unit of meters per second squared. To model this accurately, we must distinguish between average velocity, the total displacement over total time, and the precise state of the object at a specific moment. Instantaneous velocity is speed and direction at a single point in time. When this race car brakes, we track a rapid drop in its instantaneous velocity. Equations of motion rely on these specific instantaneous values, the initial and final states, to map the progress of a physical system. Because acceleration determines the exact rate at which velocity evolves, it allows us to calculate the future coordinates of an object with mathematical certainty. This graph plots velocity against time, providing a visual record of an object's linear motion. The steepness, or slope, of this line represents the change in velocity divided by the change in time. Therefore, the slope of a velocity time graph is the measurement of acceleration. An upward slope indicates positive acceleration, while a downward slope indicates the object is decelerating. While the slope provides acceleration, the area between the plotted line and the time axis reveals a new dataset. Because displacement is velocity multiplied by time, the geometric area under this curve represents total displacement. Multiplying height by width yields the total distance shifted. By breaking complex paths into basic shapes like triangles and rectangles, we can calculate the displacement of any journey using simple geometry. A single two-dimensional plot houses the entire physical history and the future trajectory of an object's movement. We use specific tools for systems where acceleration remains constant, a state known as uniform linear motion. This constant acceleration motion is governed by a framework of three primary equations. These equations utilize 5 variables: displacement, initial velocity, final velocity, acceleration, and time, often summarized by the acronym SUVAT. These formulas derive directly from the slope and area of a velocity time graph. For a sprinter starting from rest and accelerating over 50 meters, we identify our knowns: an initial velocity of 0, constant acceleration, and a 50-meter displacement. By selecting the equation that relates velocity and displacement without requiring time, we can solve for the sprinter's final speed. Algebraically isolating the unknown variable allows us to calculate exactly how fast the sprinter is moving at the end of that 50-meter stretch. Whether applied to a sprinter, a vehicle, or a falling object, these equations provide a reliable way to predict motion in any uniform system. We can apply this exact same horizontal logic to vertical movement simply by rotating our coordinate system by 90 degrees. This shift allows us to model motion under gravity, the most common application of linear kinematics in the natural world. Near the Earth's surface, gravity acts as a constant downward acceleration, denoted by g, at approximately 9.8 meters per second squared. Our variables adjust for this vertical domain. Horizontal acceleration becomes g, and horizontal displacement s is measured as height h. It is a common misconception that heavier objects fall faster. However, in a vacuum chamber, a bowling ball and a feather dropped simultaneously will hit the ground at the exact same moment. While air resistance affects how objects fall in our atmosphere, kinematics shows that the gravitational constant g applies to all objects equally, regardless of their mass. Mass is a property used to calculate forces in dynamics. In pure kinematics, gravity is treated as a geometric constant that dictates the rate of fall for all matter. We can derive this constant ourselves using the free fall method in a laboratory setting. By dropping a solid steel ball from a measured height and using photo gates to precisely record the time of the fall, we establish two precise data points: height and time. Because the ball starts from rest, the initial velocity is 0, causing the first part of our second kinematic equation to drop out. We then rearrange the remaining terms to solve for g. With just a ruler and timer, we can mathematically determine the fundamental acceleration of the planet. To master these calculations, remember the core tools: the distinction between scalars and vectors, the slope and area relationships of the velocity time graph, and the three kinematic equations. Before beginning any calculation, ensure you have clearly defined your initial frame of reference. By applying vector logic and the SUVA key framework, the path of any object moving under constant acceleration can be determined with mathematical precision.